So, we talked about volumes of solids of revolution in class, and we talked about how we can take that two-dimensional region, revolve it around an axis, and create a three-dimensional volume. And we called it the disk method because we were slicing it up into cylindrical disks that then we can accumulate all that volume and put it together. Well, what you noticed yesterday, what you might have noticed yesterday, is every time we revolved it around an axis, it was a completely solid figure. There was no hole, there was nothing missing. We broke it up into disks. Well, today we're going to look at what happens if we break it up into if we have a hollow region in our volume. So we call this the washer method. This does not mean like washer, like the washer that washes your clothes. The washer method is looking at, like in your toolbox, a little washer. It's like a thin metallic disc with a hole in the center, or you call it the donut method or the bagel method. The idea is we have this volume that's missing. So let me show you, before we get into more of the notes, let me actually show you a picture on Delta Math. So here's an example of a problem where you have, this is your solid region right here. It's formed by enclosing x cubed, x to the 1/3 power minus 2 and 1/4 x minus 2. So that is these two pieces. And we're going to revolve it around the horizontal line y equals 1. So let me move my slider and show you what happens when I do that. So my region, as I revolve it, you have this missing part. You have this hole or this hollow region that when I figure out my volume, I don't want to include that. So you get something that looks like this. It almost looks like a sideways volcano. So to do this problem, we essentially need to subtract out the volume of the hole. So going back to my notes here, so as we said, it's going to be used when a region contains a hole or some sort of hollow region. You won't really know until you actually look at a sketch or look at a picture if there's a hole there. What you're trying to see is if my shaded region, my two-dimensional, is flush up against my axis of revolution, it's going to be a full solid. If I have that missing, that gap, it's going to create a hole. So this time, instead of just talking about my radius, we're going to talk about two radii. We're going to call R, capital R of X, my outer radius. Sometimes I call it the big radius, as if there was no hole there. And then my little lower case r, or my small r, we call that the inner radius or the smaller radius. That's going to be the radius of the hole. That's the part that we don't want to include when we're figuring out the volume. It's the part that's missing. So if we revolve it around a horizontal axis, which is the most common, essentially you're doing it still all in one integral, but it's your integral from a to b of your big radius squared. That's going to give me the whole thing. And then minus the small radius squared. That's going to give me the radius of the hole. So if you kind of think of it as a picture, see if it'll let me draw here. So you can kind of think of it. So let's say we have this region up here, and we're revolving it around the x-axis. When you draw your radii, your big radius is going to go from your axis all the way to the end of the shape. And then your small radius, which I'm going to do in a different color, is going to be here. And I like to use two different color pens and pencils when I do this so I can show that big radius and that small radius when I revolve it. If I go around a vertical axis of revolution, well, now everything is in terms of y's. I still have my big radius squared minus my small radius squared. And let me show you what this looks like. So we would have, let's say we're going around the y-axis. So let's say we have this shape right here. And we're going around the y-axis. So now my big radius is going to go from the y-axis all the way out. And then my small radius is going to go from the y-axis to the beginning of the shape. So again, a big radius and a small radius. You always put your pencil on the axis of revolution and then draw perpendicular from that to draw each radius. So here's our first one. We're going to look at what happens when we take the region bounded by x squared and the square root of x. So here's my region. It's like this little petal piece. And we're going to revolve it around the x-axis. I don't have a great image of the three-dimensional region. I kind of show you just like a part of that petal as it revolves. So when I mark it up, My big radius is going to go from the x-axis out to the top function. That's going to be my big radius. And then my small radius is going to go from that axis to the bottom function. So there's my big radius and my small radius. My boundaries are going to be when I start slicing it and when I stop slicing it, just like it was with yesterday. So my boundaries for this one, you can find by either setting them equal to each other or using your calculator. Here's what it looks like when you set them equal to each other. My boundaries are 0 and 1. Big radius is the square root of x function. Small radius is the x squared function. And again, our focus really should be on setup more than it is on the actual answer that just comes from your calculator. So this would be our setup, integral from 0 to 1. Don't forget the pi out front. Big radius squared minus small radius squared, and then punch it in your calculator or clean it up first, and you get 3/10 pi or 3 pi over 10 or 0.3 pi. So that's the difference really with today is now we have this region that we want to make sure we don't include, so we subtract out. If it's in terms of y's, then hopefully it's going around a vertical axis, and that's what this one is. This is going around the y-axis. So this one is y squared and y cubed. So your y squared is the red one. Let me kind of color code this. So this is in red on my picture, and my y cubed is in blue. And I'm taking this tiny, tiny sliver and I'm revolving it around the y-axis. So this very, very, very small sliver. And when you do that, I do actually kind of have a decent picture. To me, it looks like a very, very thin funnel. And we're trying to, again, find the volume of that really, really thin funnel. So when I draw my radii, my big radius is going to go from the y-axis all the way out, and that's going to go to the red function, which is the y squared one. And then my small radius is going to go here. And we have our boundaries they actually tell us our boundaries are 0 and 1. They are y boundaries. They're where I start and end my slicing. So big radius, small radius, setup, 0 to 1 integral, y squared squared minus y cubed squared. You could square those out, or you could just put it in your calculator as is. You don't have a very big answer to 35th pi because it's a very, very thin region that revolved around. You actually have more being subtracted out than what you actually have going on there. This one, we actually looked at this in a different version. I know it says from the book. We haven't been using the book, but we actually did the part of this one the other day. So this one is taking the square root of x function, which is the red one, y equals 0, which is just your x-axis, x equals 4, which is the vertical line, and we're going to revolve it around the y-axis. So it's going to look something like this. So you're taking that and revolving it around like this. This one always reminds me of the machine that you see when you're in like Dairy Queen and they have that donate money to Children's Hospital. And it's this big cylinder that has this dip in the middle that just funnels all the way in and your money goes in and it goes round and round and round, drops in the hole. That's what I always think of when I do this one. So when I draw my radii, my big radius is going to go from here all the way out. My small radius is going to go from here until we get to that curve. My boundaries, so I'm slicing vertically, so my lowest boundary is 0. The highest boundary is 2 because that is the highest y value that ever shows up. And if you want to know how to get that, put 4 into your y equals the square root of x function, and you'll get 2. So here's my setup. My big radius is 4. My small radius is y squared. It does have to be in terms of y if we're revolving around a vertical axis. My setup is the integral from 0 to 2. Don't forget to put the pi out front. Big radius squared minus small radius squared, which gives you 128 pi over 5. So again, vertical axis of revolution, everything's in y's. Horizontal axis of revolution, everything's in x's. This is a continuation of that problem. So exact same setup, still the same functions, so same initial picture. But now instead of revolving it around the y-axis, we're going to go around the vertical line x equals 6. So it's going to look like this. So x equals 6 I kind of have as like a purplish line going down in the middle. And you get, to me, it reminds me of like the top of a bagel. So it has a really flat bottom on it, but then it has a rounded top. So my axes, drawing them, or my axis of revolution is vertical, so I do need to be in terms of y. My big radius is going to go from the axis all the way out to the end of my little bagel here. And then my small radius is going to go from there out to there. My boundaries, I'm still going from 0 to 2. That does not change. I'm still working in y's, so that's my lowest slice to my highest slice. And my setup looks like this. My big radius is going to go from 6 to the y squared. So we always do right minus left. So 6 minus y squared. And then my small radius, right minus left, is going to be 6 minus 4, which is 2. And it always, that center of the bagel basically is consistently a radius of 2. So my setup, big radius squared minus small radius squared, boundaries are 0 and 2, multiply by pi to get my answer. You do not need to simplify this in any way to get your answer. And I think that's a perfect place to stop this video.